Hello, my name is Alejandro Gómez-Londoño, and I'm presenting our work in the space called Semantics for CakeML programs, titled Do You Have Space for Dessert? First, let's discuss what CakeML is. CakeML is a functional programming language with a proven correct compiler that is able to bootstrap itself. What this means is that using the CakeML compiler, we can generate from a source program machine code and be sure that the behaviors of those two programs are compatible. What we mean by compatible in this setting is that the behaviors present in the semantics of the machine code are also present in the semantics of the source code. Or in other words, the behaviors of the source code are a superset of those of the machine code. This allows us to translate safety properties from one side to the other. However, there is a catch. You may have noticed that the source semantics is enclosed in this extend with resource limit function. What it does is that it takes the behaviors of the source semantics and extends it with running out of memory behavior. We need this because the source semantics cannot run out of memory. So we would like to replace the subset relationship with an equality. This will allow us to not only translate safety, but liveness properties from one side to the other. The approach we took was to devise a safety predicate over the source program that ensures that the compiled machine code will not run out of memory. This eliminates the need for extend with resource limits. We set out to do this with the following objectives. First, we want to make space reasoning possible in CakeML, while still producing tight and concrete bounds. And finally, being able to transport liveness properties from source to machine code. This paper's contributions are a formal space code semantics for CakeML, with a proof of soundness with respect to a compiler that relies on garbage collection. And then finally, to showcase our work, we prove concrete and tight bounds for a number of examples, non-terminating functions, higher order, and even a big num library. So why do programs run out of memory anyway? First, it may run out of heap. This is when a single or a set of objects grows so large in size that they exhaust the available heap space. Alternatively, it may run out of stack. Here, a large number of yet-to-return nested functions fills the stack completely. And finally, and perhaps more exotic, it's when an object exceeds its representation limit. For example, if an array representation uses, say, 3 bits in its header to keep track of its length, one can exceed this representation by simply concatenating two arrays of length 6. So where do out-of-memory errors appear in CakeML? The structure of the CakeML compiler, unsurprisingly, looks like a cake, in the sense that it has many layers. Each layer corresponds to a phase or an optimization. This approach keeps things modular for both proofs and implementation. The higher in the stack, the more tractable and high-level a language is, while lower levels are more concrete and close to machine code. When it comes to the representation of memory, it is worth noting that the first 6 languages in the stack have semantics that lack any form of out-of-memory behaviors. Or in other words, their memory models have unlimited space. So the relationship between the behaviors of these languages is an equality. It is only at the point where memory becomes more concrete that the subset relationship is introduced. It is also worth noting that all the languages at the bottom have equality as its relationship. So when we consider where to do our space reasoning, the first obvious candidate was CakeML. It is the source language after all, and is what we use to write our programs. It is high level, so one doesn't have to deal with allocation or pointers as much as in other places. However, the initially great upsides very quickly turn into downsides. The thing is, extending the source semantics to accommodate a space reasoning at such high level in the stack requires you either to have a complex semantics that contains basically all the compiler phases of optimizations within it so that it can be tight, or throw that out the window and provide a very loose upper bound. Both of these alternatives did not meet our objectives, so we went back to the drawing board. We noted that among the high-level languages, DataLag had a number of interesting features. First, DataLag is an imperative language, so it's easy to step through each instruction and see what effects it has on memory. it provides abstract values, which means not everything is represented using words, and there's still a bit of a structure to values. It also has a stateful storage, so you have variables instead of just bindings. And finally, and perhaps more important, it has an explicit call stack, unlike anything above it. So, pretty much everything we need to be able to reason about running out of memory is here, in a concrete enough way so we can talk about it. We have a stack, we have a heap, and we have variables and values. So DataLag also gets bonus points for being at a place in the language stack where most optimizations and tricky compiler phases have already happened, simplifying our task greatly. However, DataLag is not source CakeML, and there is of course a clear downside from writing your programs on one language and having to reason about it in another. But we have improved our infrastructure to accommodate this task as much as possible. Let us consider the example FullL, implemented in the source language at the top and in the compiled DataLang at the bottom. Variables in DataLang are numeric, so to better show the similarities, we replace them here with their corresponding source names. However, the relationship between them is still one-to-one. So the DataLang version of FullL first is displayed using a monadic representation, which improves its readability. Additionally, function names are preserved all the way from source into DataLang, so it's easy to know what is what. For the code itself, arguments are the same, they're just passed in reverse. The first few operations are a case distinction over the list argument L. If L is nil, we return the base value, just like in the first pattern of the source function. Otherwise, we are in the cons case. Here, we compute the head and the tail, followed by a call to our function f, which generates the new base value. Finally, a tail recursive call is performed with the tail, the new base value, and the original function f. Here, we can see that the original structure of the function FullL was preserved all the way to DataLang. And in our experience, this extends to most functions as well. However, some understanding of the DataLang language might be required. On that note, let's talk about DataLang values. Values in DataLang are represented by this data type. We have unbounded integers, words, blocks of contiguous values with a constructor tag and a uniqueness timestamp. We also have code pointers and value pointers. As an example, let's take the list 1, 2, 3, which is represented in DataLang as follows. The first block contains the head of the list, number 1, as its first value, followed by the tail of the list, which is on itself a list, and is represented with a block as well. The tail follows the same structure as before, with the first element, number 2, being the head of the tail, followed by the tail of the tail. You can see how the original structure of the list is represented using blocks. It is also worth pointing out that each block represents a constructor which is defined by the tag value, and that each non-empty block has a unique timestamp. So, the semantics of DataLang is defined using a functional big step semantics. It takes a program and a state and returns a result with an updated state. The state contains everything you need to execute the DataLang program. Here, we display only the fields relevant to our memory model. First, you have the locals, which contains all variables in scope for the current function. Next, you have the stack, which is the call stack, followed by the refs, which is a map from pointers to values. And then lastly, we have globals, which contains global values that can be accessible from anywhere. We can see from the state that even though the DataLang's memory model is unbounded, one can still see both heap and stack. So, to keep track of memory consumption, we extended the state with a number of extra fields. First, we added limits, which contains concrete bounds for heap and stack, followed by save for space, which is always initially true and signals when a program has surpassed the limits established. We also have stack max, which records the maximum stack size we have seen during execution. With this, we have everything we need to measure and keep track of memory. So, how do we do it then? The main idea is to measure the size of both heap and stack at relevant points during execution. We measure heap at every allocation and before every heap consuming operation. For example, the addition of two big nums, which might require allocating some extra space for its result. The size of the stack is measured at every function call, and as before, on each stack consuming operation. These are operations that are implemented in lower languages either recursively or as multiple function calls. By doing this, we can make sure that space consumption remains within the limits, or in case it doesn't, save for space will be set to false. As an example, let's see the measurement of stack size that is performed after a function call. First, we make a conjunction with the current value of save for space. Then, we measure the current size of the stack and obtain the maximum between this measurement and the largest previous measurement. We check if this new stack is within the limits and update save for space accordingly. Finally, we update a stack max to reflect the changes. Conversely, this is the measurement of heap size before a heap consuming operation is performed. Again, we make a conjunction with the current value of save for space. Then we measure the amount of heap performing the operation will require. This is the size of the current heap plus the space needed to perform the operation. A space consumed is a characterization of the space needed to perform an operation in terms of its arguments. Finally, we check if our new heap is within the limits and update save for space accordingly. These extra measurements and checks are the only changes made to the semantics. No new behaviors were added, and in fact, if one ignores the new fields, the final result is the same as it was before the changes. If save for space is false at any point during execution, the semantics will continue evaluating as normal. However, the state of the final result will contain, via save for space, an indication of whether or not our program has run out of memory. So, how do we count? We measure values using the function Sizeof. It takes as arguments a list of values, a mapping from numbers to values, which is what pointers are pointing to, and a set of timestamps. Sizeof traverses the list measuring the size of each value, but it makes sure to avoid counting the same pointer multiple times and mitigates aliasing of blocks using timestamps. To see how this works, let's briefly recall how values are represented in DataLag, and specifically how blocks contain not only a list of values and a constructor tag, but a uniquely identifying timestamp. This timestamp is important, since the semantic ensures that if two blocks have the same timestamp, their contents must be the same, because they are the same value in memory. In this example, we're measuring the size of two blocks. We assume scene is initially empty and refs is the one currently in the state. The size of the first block is 2, one word for the tag and one word for its element, the small number 1. We continue traversing the list, but the set of seen timestamps is updated with the timestamp we just saw. So when we reach the next block, we check if the timestamp has already been seen. This is indeed the case, so we don't count that block. This helps us mitigate aliasing as it stops us from counting two blocks that are essentially the same. To measure the size of the stack, we traverse it counting the size of all stack frames. So we have seen where and how do we count. Now let's consider what is it that we're actually counting. Size of heap is implemented as a call to Sizeof with a list of all reachable values. These are obtained from traversing all values in the locals, the stack, and the global references. A very nice side effect of this is that our measurement of heap size is idempotent with respect to garbage collection. We have everything we need now. Let's put it all together. Our safety predicate is then defined in terms of the evaluation of a DataLag program. We say that a source program is safe if the evaluation of its DataLag representation is safe for space. We have proven that if a program is safe, no out-of-memory behaviors can occur in the machine code, which implies that the relationship between source and machine code can be proven to be an equality. All proofs were formalized using the whole fourth theorem proven in the context of the CakeML project. So, in conclusion, we use DataLag as a space called semantics for CakeML, which makes precise measurements using the function Sizeof, that takes into account timestamps to mitigate aliasing, and by only considering reachable objects, it's idempotent on their garbage collection. So we can now answer if our program has space for dessert. This has been our work. Thank you for watching.